Okay, welcome back. First thing for today, we're going to talk about derivatives and integrals and what happens to our units. So I've got our function here, which is in kilometers per hour, and we've marked how fast our car is going in kilometers per hour every hour after leaving home. So all of these dots are how fast the car was going in kilometers per hour after hour 1, then 2, then 3, then 4, then 5. And I've also tracked all of the time in between, so we get a nice function out of it. So the first thing I want to do is get the slope. If I wanted to get the slope, what would happen to my units? Okay, I don't think the microphone caught, so I'm going to repeat that really quick. So, what's going to happen to our units? Anytime we get a slope, we're really getting a change in y over a change in x. So if I'm getting a derivative, I'm getting a slope at a point. So my change in y over change in x for my units is going to be kilometers per hour divided by hours. If I wanted to look at it graphically, this is slope at a point is the same thing as the slope of the line tangent to the curve at that point. So if I wanted hour 3, for instance, here, my slope would be my change in y over change in x at that point. So that's change in kilometers per hour over hours, which if I divide out gives me kilometers per hour squared. Okay, if I wanted to take a look at the integral, I would be getting the area underneath the curve instead. So that would look something like this. So my area under the curve is really an infinite series of rectangles that we are adding together. So tons and tons of tiny rectangles like this. That I am adding together, so to fill up that space. And each rectangle has an area of a base times height, which means to get the area I'm really multiplying my y units times my x units. Now if each of these rectangles is infinitely small, then I'll get closer and closer to the actual area. So if I make these rectangles even smaller, I'm closer to getting the full area of that space. If they're infinitely small, then I'll just be drawing a series of lines instead of rectangles, which will give me the perfect area underneath the curve without any error. Okay, so the area under the curve is really just infinitely many rectangles that all have areas of base times height, which means the units for this area underneath the curve are going to be the units of y times the units of x. So in this case, that would be kilometers per hour times hours, which leaves me with kilometers because our hours cancel. So this is going to tell me the displacement of my car over time. I've been a little bit careful with that. This is displacement, not total distance traveled. And the reason why is because it's possible for us to have a negative velocity. If I had a negative kilometers per hour, that means I would be traveling in the opposite direction. So if this is leaving home, if I started to go back towards home, that would be negative kilometers per hour. My displacement would tell me how far away I am from the start point, not how far that I've traveled. So if you're looking at a car, on the inside of a car you usually have an odometer, which looks something like this. It's a little gauge that tells you how far your car has actually traveled in kilometers. So maybe this car has traveled 15,587 kilometers. And that continuously goes up forever, as long as the car keeps driving. Doesn't matter what direction the car is going in. If you wanted that, so you would want the total distance traveled instead, which would be equal to your integral of the absolute value of your function in terms of x. So if we don't care about direction, then we'll get the total distance traveled instead. From A to B. Okay. So if I want to do that, my units are still y times x, so I'm still looking at kilometers. But because I've taken the absolute value, any negative values, anything below the curve, would end up being positive instead. Okay. When we're talking about, to use distance as an example, when we're talking about distance, velocity, and acceleration, we have scalar quantities and vector quantities. Scalar versus vector. Which might be new vocabulary for some of us. So scalar quantities are ones that do not have direction. Vector quantities do have direction. So the scalar for distance, I'll write units in here too. So units. Okay, so if I wanted to look at, we'll say meters, for instance. I'm just going to write m for now. My scalar for meters, that's if we don't have distance, if we don't have direction, rather, is going to be my distance traveled. If we don't care about the direction, then I'm just looking at distance. If I do care about the direction, we're looking at what's called displacement, how far away an object is from the start point. Okay, then if I derive meters in terms of time, I would get something like meters per second. So the scalar of meters per second would tell me speed. So speed does not have direction. And the vector unit would be velocity. Velocity is speed with direction. So velocity can be positive or negative, but speed is always positive. If I ask you how fast the car is going, I'm not asking you what direction the car is going. But if I ask you what's the car's velocity, you need to tell me we're going 30 kilometers per hour north. Okay, and the last one, if you derive velocity, you get acceleration, which is meters per second squared, which I don't have a good way of writing in this program, so I'm just going to add that here, meters per second squared. The scalar of meters per second squared, we don't have a word for in English, so we call this the magnitude of acceleration, which is a mouthful, but gets the point across. And then the vector is acceleration. Okay, in AP Calculus, very rarely, but sometimes we'll derive this one more time. So if I derive acceleration, I get meters per second cubed. Which is called jerk. Make this lowercase to match everything else. Okay, jerk is a vector, meaning it has direction. Again, in English we don't have a word for the magnitude of the jerk, so we actually have to write it out. The magnitude of the jerk is going to be my scalar quantity of the derivative of my acceleration. Okay. Any questions on what we've done here? If not, I'm going to shrink this up a little bit and clean this up so we can pass it on to everybody else. This is, oops, this one, I think. There we go. Okay, and then I need tools. And then we'll copy all of this one over here. Alright, lost the T right there, so I'm going to add that displacement. Okay, so that's pretty much everything we need to know about our units. I'm going to give us another one and we'll see how we do. So let me save this up for us really quick. Let's see, this will be area. And then we'll do one more with the opposite one showing. So this is slope. Alright, so if I get rid of all of this, let's see, I'm going to copy just this part into a new layer so that we still have it as a reference. And then we'll get rid of everything else. Oh, I see. Okay. Oops. How should I do this? I need to do this, I think. Copy this part first, and then just copy the top. Alright, there we go. So I'm going to change our units for this. Instead of kilometers per hour and hours leaving home, we're going to look at hours of continuous sleep versus ounces of milk fed to a baby before bed. Okay, so this is a special experiment for everyone who has newborn children. We're going to try to get the most amount of continuous sleep for our child at night so that we don't have to keep waking up and changing diapers and stuff, with the right amount of milk. So this is something, if I had a kid, I would be doing with the first couple weeks. So kind of trying to track and figure out how I can get the most sleep out of this. So to do it, I'm going to start out just tracking how long they actually slept for. Should really be in minutes instead of hours, but how long they slept for continuously, and how many ounces of milk I actually fed to the baby. And what we're going to try to do is maximize this. So what amount of milk will give us the maximum hours of continuous sleep? So the first thing I need to do is derive this function. If I derive this function, what will my units be? Close. Slope is change in y over change in x. So what should this be? What's my change in y over change in x for my units? If we make a substitution. Okay, y is hours, so my hours should be on top. Hours per what?
Per on.
Right. So this is how many hours of sleep do we gain for each additional ounce of milk that we give to the baby. So at the point where the hours of continuous sleep that we gain per ounce is equal to 0, I will either be at a relative maximum or a relative minimum. And what that means is if the hours of sleep that we are gaining per ounce is equal to 0, that's my slope of this function is equal to 0, which it is at all of these points that I'm drawing now. I will be at a relative maximum or minimum, which means relative to the points around it, I'm either at a high point or a low point. And you can see a problem, right? We have a lot of maximums and minimums. I'm going to label these really quick. This is point A, point B, point C, D, E, F. Okay, if I want to maximize the baby's sleep, which one am I actually looking for? Which point? Okay, I've got 4 relative maximums, A, C, E, G. You need to choose C. Okay, how did you do that? How did you know? Okay, you chose C. Chose C because you knew it was the maximum. Okay, so let's break that down just a little bit. What told you that C was the maximum when you looked at the graph?
The longest number of hours.
Longest number of hours. Okay, so you're looking at the y value. You're looking at which of the relative maximums, so A, C, E, or G, had the largest y value. Okay, so to find a maximum, an absolute maximum, which is the highest point on a graph, we would need to do 3 things, actually. So I'm going to erase the stuff that we have on the side. All of which you just did in your head, actually. This one, there we go. So the first thing we need to do to find the absolute maximum which is the highest possible point on a graph. Okay, so number 1, derive the function and set it equal to 0. So this gives us all of the points where the function changes direction. So that gave us A, B, C, D, E, F, G. Okay. Number 2. We need to test to see which of these points are relative maximums. Either sign change from positive to negative of f prime of x, so of the first derivative. If the first derivative changes from a positive slope to a negative slope, that is a relative maximum. Or the second derivative at that point is negative. Either of those will prove that this is a relative maximum. So if you take a look at a, c, and e, the function is concave down. So that means my second derivative is negative. Also, for all of the points a, c, and e, my sign changes from positive to negative for the slope. Either one of those can prove that this is a relative maximum. Okay, then the last thing we need to do, plug in all of the relative maximums, the start and end points, into f of x to find the maximum. Okay, I'm out of room, so I'm going to add just a little bit here. Okay, so if I actually wanted to solve this problem, I would derive the function first, set it equal to 0, giving me a, b, c, d, e, f, and g. Then I would test to see which of those points, a, b, c, d, e, f, g, is a relative maximum, either by looking at the concavity of all of those points. Anyone that is concave down with a slope of 0 is a relative maximum, that's a, c, e. Or looking at the slope change. Does the slope change around that point from positive to negative? If you have a lot of points, the second derivative test is going to be faster, so derive it one more time in general form to get a second derivative that you can plug all of these points into, and then just plug in the numbers to see do you get positive or negative. That's going to be faster than plugging in two numbers around A, two numbers around B, two numbers around C, two numbers around D, two numbers around E to see is my slope changing from positive to negative. So if you've just got one or 2 points to test, maybe your first derivative is easier because you don't have to derive again. But if you've got a lot of points, your second derivative is usually easier. Then I'm going to plug in all of the relative maximums we found, which is a, c, and e, into my original y value, into the original function. And that will tell me what is the y value at a, at c, and at e. Okay. I'm also going to plug in my start point and end point, because it's possible that my function does something crazy like this. If my function did this, so came back up afterwards, even though this is not a relative maximum or minimum, my highest point is now at the end, right? Okay, that would throw us off. So in case this happens, I also need to test the start point and the end point. Once we plug in all of our relative maximums, the start point and the end point, the highest y value out of all of those will be the absolute maximum value. Okay, so that seems like a lot of work. But really, we only had to test 5 points to figure out the largest possible y value of infinitely many points on this function. So even though that is a bit of work looking for the derivative and maximizing this function, we really only test 5 points instead of all of them, which is nice. Any questions on what we did? Okay. That's called optimization. If I was going to find the absolute minimum, I would do almost the exact same thing. So let me flatten this, and then I'll turn this over to you, and you can tell me what we would do to find the absolute minimum. Save this one here. This is optimization maximum. Okay, so based on what we just did, if I wanted to find the absolute minimum, what do you think we would do?
I need to find out the compatibility. I need to find out the things that flow from
Okay, you're right, we need to get the derivative. Okay, so the first thing we need to do is derive the function. Then what?
So grab the function, find out the absolute minimum.
Okay, how do we do that though? How do you find the absolute minimum? How do you find the relative minimums first?
Based on the concavity.
Okay, before that, how do you know which points to test for concavity? What has to be true about the slope first?
We need to find the slope. So we need to find out the change of slope from equation to equation.
Okay, we need to derive the function that gives us a slope at any point. Then I'm going to set the slope equal to what? 0. Okay, there we go. So derive the function and set f prime of x equal to 0. Then solve for x. This gives us all the points where the slope is 0. 2. Determine the relative minimums by either testing f prime of x, testing if f prime of x changes from what to what. If this is a relative minimum, what will happen to our slope at that point? Not decreases. The slope at the point is 0, but okay, it's going to change from negative to positive. From negative to positive. The other way that I could do this is use our concavity. So what will the concavity be for a relative minimum?
Concave. It has to be concave. Up and concave up.
So if the second derivative is positive and f prime of x is 0, it is x is a relative minimum. There we go. 3. So now I know all of the relative minimums. What's the last thing I need to do to find the absolute minimum?
So we need to plug.
Okay, plug in all relative minimums. And what? I think I just said it. And the start and end points. Oh, I'm out of room. Okay. I'm just going to reduce this. And these start and end points to determine width. Oh. Plug in all relative minimum and start and end points into f of x to determine which has the lowest y value, which is the absolute minimum. Alright, so if I did that really quickly, graphically, I would derive the function and set the derivative equal to 0, which gives me a, b, c, d, e, f, g. Then I would determine the relative minimum, either by testing the slope to see around all of these points. Does the slope change from decreasing to increasing? So for A it does not, for B it does, for C it does not, for D it does, for E it does not, for F it does, for G it does not. Okay. I could also check the concavity. If I am concave up with a slope of 0, which is B, D, and F, then I have a relative minimum. Okay, so now I've got 3 points, B, D, F, but I also need to check the start point and the end point. Again, because it's possible for the start points to be lower than my relative minimums, which for this function it actually is. Our start point is 0, and B, D, and F are all positive. So that tells me that the lowest y value, if I plug in the y value of B, D, and F, which are all positive, and my endpoint, which is positive, my start point, which is 0, my lowest value out of all those is 0, which is my start point. So my start point is my absolute minimum. Okay, any questions on what we did? Very clear, awesome. Okay. Let's go ahead and try one problem, because we've got about 12 minutes left. Okay. This will work. Okay, so can you see?
So 3x to the...
Yep. I'm going to copy this and paste it to the Skype chat in case we lose connection, so you've still got the problem. I believe I'm covering the chat window up, so let me do that. Okay, so question is posted to the Skype chat, and then I'll throw this in Word so we can work on it. Okay, so for part 8, I want to know what intervals is this function increasing. So what do I have to do to find when this function is going to increase?
I need to find out when is the time it changes
Okay, I need to figure out when this is going to change from positive to negative or negative to positive. How do I find out the slope of this function? What can I do? We need to derive. Awesome. Okay, so if I derive this function, what's going to happen?
I will compare the power.
Okay. So if I derive this, f prime of x is equal to what?
That will be
Okay, 15x squared, or 15x, sorry, to the 4th power, minus 15x squared.
and then I can factor.
Okay. So we'll simplify this. So f prime of x is equal to what?
So I have values of x is 0.
Okay, I think you're a step ahead of me, but you're right. So we factored out 15x squared, so that's 15x squared times x squared minus 1. And then you set this equal to 0, and solve for x. So if I've got 0 is equal to 15x squared, or 0 is equal to x squared minus 1, what could x equal? What values of x will make this equal to 0?
For that, it's positive or negative.
Okay, so x equals 0 or x equals positive or negative 1?
Negative and positive.
Awesome. So I've got 3 points where this is equal to 0. So that means I've got 3 points that I need to test. So I'm going to draw out a number line really quick, and we'll test this. So grab this shot. And we'll keep going over here. So here's what we had from Word earlier. I want to test points around this function. At the points 0, 1, and negative 1. Okay, so if I plug in a point that is below negative 1 into our derivative, will my answer be positive or negative? So let's plug in negative 2. If I plug in negative 2,
it has to be positive.
It'll be positive, okay.
The result.
What if I plug in negative 1/2?
It's still be positive.
Okay, let's try that again. So if I plug in negative 1/2, negative 1/2 times negative 1/2 is 1/4, minus 1 is negative. So I've got a negative times a positive, gives me negative. Okay, what about positive 1/2? Negative, okay. And if I plug in 2?
Positive.
Positive. Okay, so I could say that my graph is changing from increasing to decreasing, from decreasing to decreasing, and then from decreasing to increasing, about these points where the slope is equal to 0. It would be easier to get rid of this part. Just copy that. Okay, so let me come back into our Word document and we'll keep going from there. So we just created this this first derivative test. I'll label it first derivative test. About the points where the slope was equal to 0. So now that we've done the first derivative test, I want to know on what intervals is this function going to be increasing. So when is our function increasing, if these are the only points where the slope can change?
It's increasing on a number less than negative 1 and a number bigger than 1.
Okay, so I could say our first derivative is greater than 0, which means we're increasing on the interval from negative infinity until negative 1, not including negative 1. And the interval from 1, not including 1, to positive infinity, which is exactly what you said. As long as I am below negative 1 and as long as I am above 1, but in interval notation. Okay. I might add commentary later because we're running a little low on time. So let me add one more below here. I also want to know what intervals the graph is concave up. So how can I tell whether a function is concave up or down? Find the second derivative. Okay, so we need to derive this again. So I'm going to go to our first derivative that we had up here, and we'll derive that. So I'm going to copy the first derivative down here so we've got it all together. And we'll derive that one more time. So what happens if I derive this first derivative? Okay. Perfect. Is there anything that I could factor?
Oh yeah, I need to factor 30.
Okay, so that gives me 30x times 2x squared minus 1. Okay, so we were asking where are we concave up? So what's the next thing I need to do?
I need to just like 0, so I can take the x from x to 0 and then positive and negative.
Very close.
Oh no,
So-
square root of positive and
Okay, you're right. So x is 0 or x is positive or negative square root of 1/2. So that's 1 over square root of 2 or root 2 over 2. Okay, so that gives us 3 points to test. And we're going to do the same thing that we did last time, only with our second derivative test. So copy this over. And we'll shrink it a bit to give us some room to work. Okay. So once again, we've got 3 points to test. At x equals 0 and x equals negative root 2 over 2 and positive root 2 over 2. Which I think I'm just going to copy this for the sake of time. And 0, and then we'll get rid of the signs we don't need. So this is negative root 2 over 2, and this one is positive root 2 over 2. Okay, so scroll back up so you can see our equation here. I need to know if I plug in a point that is less than negative root 2 over 2, will my answer be positive or negative? So I'm going to pick one that I know is less than negative root 2 over 2.
It's negative. It's negative. If I was negative squared into over through the 7 it's negative.
Okay, if we plug in negative root 2 over 2 directly, we'll get 0. Because this would be root 2 over 2 times root 2 over 2 is 2 over 4, which is 1/2 times 2 is 1 minus 1 is 0. So all of these points, if I plug them in directly, will give us 0. I need to know what happens if I plug in a point that is less than negative root 2 over 2, so let's plug in negative 10. If I plug in negative 10, what's going to happen?
It's going to be negative.
Okay, it's going to be negative. Then I need a point that I know is between negative root 2 over 2 and 0. So let me stop for a minute. Roughly, what is root 2? Or can I squeeze the square root of 2 between 2 points? What's the square root of 4?
Square root of 4 is 2.
Okay, the square root of 4 is 2, and the square root of 1 is 1. So the square root of 2 must be some point between 1 and 2. So this is some point between 1 and 2. So if I plug in negative 1/2 into our function, we should be okay. So let's plug in negative 1/2. That'll be a point between 0 and negative root 2 over 2. So if I plug in negative 1/2, 30x is going to be negative. If I plug in negative 1/2 into 2x squared minus 1, that'll give me 2 times 1/4 minus 1. Is 1/2 minus 1 is also negative. So I have a negative times a negative, which is positive. Okay, same thing over here. We know root 2 is between 1 and 2. Because the square root of 1 is 1, the square root of 4 is 2, so the square root of 2 must be between them. So if this is some number between 1 and 2, then 1/2 will be between 0 and root 2 over 2. So if I plug in positive 1/2, I get a positive number times a negative number is a negative. Okay, last one. If I plug in positive 10, what do I get? Okay. Awesome. So we've got our graph with all of our points. So I'm going to copy that over. Okay, looks like that was just enough to kick me off the page. So let me shrink this just a little bit and give us some room for the margins. There we go. Alright, so we did our second derivative test. And came up with this. Okay, so our goal was to figure out where is this concave up. So based on our number line that we just created, when is our function going to be concave up? Okay, so from negative root 2 over 2 to 0, both not included. And from positive root 2 over 2 to positive infinity. Perfect. Is when we would be concave up. Okay. We're a little bit over time. Do you want to do C or do you want to save it for next time? We'll do it now. Okay. So with the equation, I want to write the equation of each horizontal tangent line to the graph of f. So a line that is horizontally tangent to our graph would be where the slope is equal to 0. So I want the equation of a line at all of the points that are where the slope is equal to 0. Okay, so we already know with our first derivative test that the slope is equal to 0 at -1, at 0, and at 1. Okay, so in order to get the equation of a line, write commentary, to get the equation of a line, we need a slope and a point. Then we could use point slope form, since the question does not specifically ask for slope intercept form. Okay, I know a lot of our students really like to keep everything in slope-intercept form, but that would mean that we have to do another step in order to solve for the intercept. And we've got 3 lines that we need to create, so that would be 3 extra steps where we could mess something up solving for an intercept and then plugging back into an equation. So this is going to be a lot easier if we can use point slope form instead. So I'm going to rewrite point slope form just in case we need it. Point slope form is y2 minus y1 is equal to m times x2 minus x1. Which, if you think about it, makes sense. If our slope is equal to change in y over change in x, so m is equal to y2 minus y1 over x2 minus x1, I could solve for my change in y by multiplying both sides by the change in x, which would give me this form, slope-intercept form. Okay, so to use slope-intercept form, I need one point, y1, x1, and the slope at that point.
Can I use a 1 and 0 and negative 1
Right. So we need the equation of the horizontal tangent line. So I'm going to plug in -1 first into our original equation. So I'm going to rewrite this part. F of x is 3x to the 5th power minus 5x cubed plus 2. X cubed. X cubed plus 2. Okay, double check. 3x to the 5th minus 5x cubed plus 2. 3x to the 5th minus 5x cubed plus 2. That's good. Okay. From part A, f prime of x equals 0 when x equals -1, 0, and 1. So I need to find the y value at those points. So we need to find f of -1, f of 0, and f of 1.
Oh, okay.
Okay.
So I can find
Right, I'm gonna move this down. Okay. So here we go. First one. What is f of -1?
I have 4. I have I have 0. Oh, what is the 0 of the function? Oh my god. Okay, it's 0.
I did not get 0, so hold on. I've got, these are all odd powers, so my negatives are going to stay negative. So I've got -3 plus 5 plus 2, right?
We're substituting with negative. Sorry, I'm doing positive 1 for you. So I have -1, so I have -3. And negative 2. So that will become... Okay, so then I have 4.
I do too, so we look good. Okay. If I plug in 0, what do I get?
I have 2.
2. And then last one, if I plug in 1, what do I get?
I get 0.
Okay, there's a 0, so... these are my... Okay, so we'll get the equation of the line horizontal of the... call it horizontal tangent line, that's what they called it. Horizontal tangent lines. So I've got... Our first one is going to be our line that is at x equals -1. So my equation of the line for that would be y minus our y value at -1, which is 4, is equal to our slope, which is 0, times x minus our x value at -1.
Oh.
Okay, so if I plug that in, my 0 gets multiplied by everything on the right-hand side, so this was x plus 1 times 0 is 0. So I have y minus 4 equals 0, or y equals 4. Okay, my next line, I've got y minus 2 is equal to my slope of 0 times x minus 0 is my x value. So that's 0 times x minus 0 is 0. So y equals 2. Okay, and last one. Y minus 0 is equal to 0 times x minus 1. So y is equal to 0. Okay, I went a little bit fast on that last part. So I'm going to write my general form for the equation of those lines one more time up here. What I just did was y minus f of x is equal to f prime at x times x minus x. Is there a better way to do this? Just to show what I'm actually plugging in. I'm going to subhead these. So there we go. Okay, so this xi is what I'm actually plugging in. So the first one would be -1, the second one would be 0, the third one would be 1. But at all of these points, the slope is equal to 0. That's how we got the points initially. So that caused the right side for all of these to be equal to 0, which meant that our horizontal tangent lines were really y values, which makes sense, right? If I'm horizontally tangent, then it should be y equals something. Alright. Any questions on what we did? Okay, in function notation, this could be written like this. Point slope form. Okay. Not a lot of commentary yet, but it looks good. So let me save this as 1992 AB1. And we'll make that a PDF as well and post that to the chat. Alright, thank you very much for coming.
Thank you to you.
I'll just finish posting these and we'll be all set. Let me stop the recording.